Well, good afternoon and welcome you all to this session of fluid mechanics. So, today we will be beginning a new chapter or a new section, introduction to turbulent flow. But before I start the turbulent flow, I just like to conclude the earlier section, that is the boundary layer, introduction to laminar boundary layer, by continuing the earlier discussion that we were discussing about the boundary layer separation, that we have recognized when the real fluid flows against an adverse pressure gradient, then what happens, the fluid particles very near to the boundary, that means the fluid particles within the boundary layer, very near to the solid boundary, because of their low kinetic energy, flows in the opposite direction, cannot surmount the adverse pressure here. And because of this, what happens that an eddies are formed. Eddies are formed because of these local flow reversal zones, and which curtails the pressure in the fluid. Therefore, the pressure in the fluid in that region becomes low, is reduced. So, therefore, when the fluid passed a body and boundary layer separation takes place because of the typical nature of the flow, that means the flow is decelerating that against an adverse pressure gradient, then the downstream part where the boundary layer separation takes place, the pressure is reduced from that in the upstream part, for which a net force which comes from the difference of pressure in the direction of flow takes place, that is known as drag force, and which is because of the boundary layer separation, and this drag is known as the form drag. Just take an example here. If we see, we are discussing that flow past a circular cylinder. We know in case of an ideal flow, parallel ideal flow past a circular cylinder, the flow is symmetric about both this and this axis. And the pressure distribution is like that from this point, this is the stagnation point where the velocity becomes 0, that is the 0 degree measured here, the azimuthal degree, that the in the azimuthal direction, the 0 degree. So, as the flow approaches from 0 to 90 degree, this half of this cylinder, it is an accelerating flow and the pressure continuously is reduced. So, this part of the cylinder, the flow is decelerated, that means the flow takes place against an adverse pressure gradient, pressure is again going to be high, and ultimately the entire pressure recovery takes place in case of an ideal fluid flow. But in case of a real fluid, the boundary layer forms near the surface. So, what happens in this region after 90 degree, when the fluid faces an adverse pressure gradient, the boundary layer separation takes place. It takes place some point near around 90 degree, even some before 90 degree angle, because of the steep pressure gradient, the flow reversal may take place even before 90 degree. So, at some point here the flow reversal starts taking place, that is the boundary layer separation, and ultimately eddies are formed, turbulent eddies are formed, and the pressure here in this downstream part is getting reduced from that in the upstream part. Upstream part pressure P infinity, which is more than P. So, therefore, what happens, a net pressure force act in the cylinder in this direction. This is so for any body. If there is another body, any body of any shape, if the flow takes place. So, you see, due to the boundary layer separation, so what happens, due to the boundary layer separation, the pressure here in this part, let this P2 and this part pressure is P1, P2 is less than P1. So, P2 minus P1 times the frontal cross sectional area A gives a force, drag force in this direction, in the direction of flow. But there is another drag force because of the skin friction, which is because of the shear stress between the fluid and the solid surface. So, this is also acting in the direction of the flow of the fluid with respect to the solid. So, to distinguish this drag force from that one, it is known as form drag, or rather it is expressed by Fp, form drag, Ff rather, form drag force. So, the total drag force Fd is composed of skin friction drag Fs and the form drag. Why? The boundary layer separation depends upon the formation of the body, shape of the body, because it is the shape of the body which dictates the adverse pressure gradient, and therefore the boundary layer separation takes place. So, that is why it is named as form drag, which depends upon the form of the body, which is due to the boundary layer separation. So, the drag force exerted by a body when it is placed in the stream of a real flow of a real fluid, then it experiences two kinds of drag force, that is the force in the direction of the flow of the fluid with respect to the body. One is the skin friction drag, which is because of the shear force between the fluid particles and the skin, that means the surface of the solids, and another is the form drag, which is the force acted on the body in the direction of the flow of the fluid because of boundary layer separation, which results in a reduction in pressure in the downstream part of the body from that of the upstream part. Now, it is very essential to reduce this form drag. So, there are methods by which we can reduce the form drags. There are two methods by reducing the form drags or boundary layer separation. One method is that by making the body streamline, that means streamlining the body, streamlining the body. Another method is by adding high energy particles in the boundary layer, high energy particles in the boundary layer, okay, in the boundary layer, high energy particles in the boundary layer. Now, streamlining body means like that if a body is like that, for example, a sphere. So, there is a boundary layer separation. So, therefore, what happens, that boundary layer forms and there is a separation. That means, if the fluid flows like this, so boundary layer starts forming like that and there is a separation. So, that the boundary layer forms and there is a separation. So, if we now make the body like this, a little elongated like this, that means we make the body streamline so that when the fluid flows over this, the boundary layer separation is delayed. The boundary layer separations are delayed. That means make the body such a shape so that the boundary layer separation is either prevented or delayed. That means make the adverse pressure gradient more flat so that the boundary layer separation takes place at almost at the trailing edge, so that the net pressure forces in the direction of flow is reduced. So, a body where the boundary layer separation is delayed, much delayed or prevented, is known as a streamlined body, whereas a body for which the boundary layer separation is advanced is known as a blunt body, which gives a more boundary layer separation, blunt body. So, making the body streamlined. Now, another way of reducing the boundary layer separation is by making adding high energy particles in the boundary layer. We have recognized that it is because of the loss in the energy of the particles within the boundary layer, because of the viscous interaction between the solid surface and the fluid particles become unable to cross the adverse pressure hill. So, that if we put more energy in the fluid particles within the boundary layer, so boundary layer separations may be avoided. This may be done, for example, by making a surface pores. For example, let the fluid flowing over a surface like this, let a surface fluid. So, if there are pores through which the particles are injected at high velocity, fluid particles tangential to this surface within the boundary layer, then what happens, the boundary layer separations may be avoided. By simply injecting fluid particles at high velocity tangential to this surface from surface pores. So, just near the solid surface, particles with high kinetic energy have to be injected, so that this helps, this gives the energy to the slow moving particles. So, as a whole, the bulk energy of the particles within the boundary layer, that is the energy of the slow moving particles within the boundary layer, gets enhanced, so that the boundary layer separation is delayed. So, there are two methods by which the boundary layer separation is delayed, so that ultimately the form drag on the body is reduced, the body experiences a less amount of form drag. So, well, now I will start the turbulent flow. We will start the today's lecture as turbulent flow. Now, we have probably mentioned in many places earlier while discussing different principles of fluid flow, that laminar flow and turbulent flow. There are two kinds of flow for a real fluid, known as laminar flow and turbulent flow. So, the concept of turbulent flow first came in the mind of Raynaud at the end of by the end of 19th century, from a very classical experiment which he performed, from where he first came up to the concept of Raynaud's number as a similarity parameter, and first he observed two distinct kinds of flow qualitatively. One is a laminar flow, another is a turbulent flow, which was named afterwards. Now, let us therefore start from that classical experiments by Raynaud at the end of 19th century, when he first demonstrated the two distinct kinds of flow. One is a laminar flow, another is a turbulent flow. Well, let us see the experiment. So, experiment is like this. He first started with a tank with a liquid, for example water. He started with water in a tank with a constant height. One tube
was attached by the side of the tank at this position with a flared NT, and a valve was kept at the downstream part of this tube, which was initially closed. Now, what if was started in the experiment? What was his basic intention? First, the water in the tank was allowed to settle coolly, so that no disturbance is there in the water, and then the entry of the water, to make a smooth entry without any disturbance of this water in the tube, the entrance of the water was made flared like this, which is known as a bell mouth entry. Then a valve was kept at the downstream to change the flow through this tube, so that the entry of the liquid takes place without any disturbance. Then what happened? He injected colored dye just at the center of this tube to see visually the nature of the flow by observing the colored dye which he injected, the position of the colored dye in the flow. So, what was observed, that as the valve was opened gradually in the region of very low flow, he observed that the flow was like this, that if this is the tube, the flow was like this, that the colored dye which was injected at the middle, it goes throughout as an unbroken colored thread. Then what happened after increasing the flow, that means if the valve is gradually opened, so if the flow is increased, it was found that when the flow increases with the increase in the flow rate, it was found that the colored dye is, which was unbroken thread earlier, gets little wavy. After some length from the inlet, it gets little wavy in nature. And still with further increase in the flow, he found that the waviness in this colored dye which was injected here, that means this thread becomes more and then erratic like this, and at still higher flow it was found that it is like this, it more or less waviness much irregularly like this, it moves like this, and still at higher flow it was found that the entire liquid becomes evenly colored. That means the dye mixes everywhere due to this movement, and the entire liquid becomes colored liquid. Though it is maintained little here, the ultimately entire liquid becomes colored liquid. So therefore, he observed that after certain flow, certain velocity of flow, the orderly motions of the fluid particles like this, gliding one over another at different lamina, this is the word from which it has come, it flows at different lamina, that means one plane gliding over other plane is distorted. That means there occurs a transverse velocity which is fluctuating with time and space, so that the thread becomes wavy, and it becomes still more wavy as the flow is increased, and at still higher flow the flow becomes totally irregular in nature. The fluctuating flow becomes totally irregular in nature, so that the entire flow becomes colored. That means the fluid particles intermingling with each other in the transverse directions, and so that the colored thread gets an opportunity to mix with the entire fluid, and the fluid becomes colored. So with this he concluded that there are two kinds of flow. In one kind of flow is this, where the fluid flows gliding over each other in orderly manner, that is known as laminar flow, and another flow which takes place at a higher flow rate, which is the turbulent flow, where the fluid has erratic fluctuations. Fluid flow has erratic fluctuation, and in this case the flow has got different dimensions. That means though the bulk flow is in this direction, the fluid particles has got a fluctuation in the transverse direction, which is absent in case of laminar flow. Now he had the idea that is it so that there is an unique velocity or the critical velocity above which it happens. Then he did the experiments with different fluid. Then he tried to find out what is the velocity range, or what is the value of the velocity, critical velocity over which the laminar flow changes to turbulent flow, and he found it varies from fluid to fluid. And also he found that it depends upon the diameter of the pipe also. and ultimately found out an unique value of this parameter, the combination of this rho Vd by mu. Rho is the density of the fluid, mu is the viscosity of the fluid, V is the average flow velocity of the fluid, and D is the diameter of the fluid, D is the diameter of the pipe, sorry. This combinedly decides the criteria after which the flow changes from one kind, that is the laminar flow, to another kind, a irregularly fluctuating flow, it is turbulent flow, and this number is known as Reynolds number according to his name, and this Reynolds number becomes the criteria for a fluid to change from its laminar flow regime to turbulent flow regime. When the Reynolds number is small, then the flow is laminar. When the Reynolds number is high, the flow is turbulent. That means when therefore the concept of velocity comes in this way, if the fluid has got more viscosity, fluid becomes laminar even at a very high velocity. But if the fluid has got less viscosity, fluid becomes turbulent even at a lower velocity. So as a whole, the combination of these parameters known as Reynolds number is the criteria for the fluid flow to change from a laminar to turbulent flow. Now, with this classical experiment of Reynolds by the end of 19th century, I now come to the concept of turbulent flow. Today turbulent flow has developed like anything, and there is a vast course for turbulent flow itself. So we will not discuss as a whole the concept of turbulent flow. For this course we will give only a brief introduction of the turbulent flow today. In almost all the flows in practice are turbulent in nature. So therefore, we must require the analysis of turbulent flow or the concept of turbulent flow analysis. Now, therefore, we first define turbulent flow in this fashion. Turbulent flow is a flow where there is an irregular fluctuations of the velocity components. That means if the velocity component exceeds some value, that means when the flow Reynolds number exceeds some value, this particular critical value depends on flow to flow situation, then the flow velocity at any point irregularly fluctuates with time. And even if the flow is one dimensional, that means the bulk flow takes place in one dimensional, there occurs these irregular fluctuating velocity components in all the directions. That means actually a turbulent flow is three-dimensional in practice. So therefore, a turbulent flow is basically unsteady and three-dimensional. That means always the motion or the velocity of a particle is fluctuating with time. That means at any point if we want to measure the velocity of a particle, we will see with time the velocity is fluctuating irregularly. This is a random fluctuation. So the flow field is associated with a random fluctuations with time. So therefore, we can express the flow field of a turbulent flow like this, that in case of a turbulent flow, for example, if we consider u, v, w as the three velocity components in case of laminar flow, we know we define for a laminar steady flow, the velocity components are like this, all right, like this. And for an unsteady flow, we introduce a time t. But for a turbulent flow, at any condition, the velocity component u is a function of space coordinates x, y, z I am telling, and also a time. And this function of time is an irregularly fluctuating function. So v is also s and t, w is also a function of s and t. Even for a steady turbulent flow, this is an irregular fluctuation with time. Velocities are functions of time, but the concept of steady flow I will come afterwards. Now let us consider an one dimensional flow. For example, u is a function of x, one dimensional steady laminar flow. But in case of one dimensional turbulent flow, it will be a function of t, and therefore velocity and Vw, there will be a fluctuating component of v, that is also you can say that is a s, that means space variable s, we can better write s and t. So this we can show like this, that there is a, if we want to show u versus t, we will see that an irregular fluctuating component. Similarly, if we plot v with t, we will see the same irregular fluctuating component. That means at any point the velocity components exhibits an irregular fluctuations with time. But these irregular fluctuations can be described statistically. This is random. This is a random fluctuations. This is random fluctuations. So that they have a correlation. Random fluctuations and they have a correlations. Now, according to Reynolds, the characterization of a turbulent field. Now it is characterization of turbulent flow field, of turbulent flow field. Now, it was Reynolds first who told or who had a guess and found from experiments that these random fluctuations are such that it can be expressed as a mean plus a fluctuating component. That means, for example, the u component of velocity can be expressed as a mean component plus a fluctuating component. What is this mean? That means, if we express the at any point, for example, the u component or x component of velocity, we can express this as this. That means, these are fluctuating over a mean value. That means, fluctuations are such that they describe a definite mean. So that the velocity can be expressed in terms of a mean plus the fluctuating component. This is the function of t. The value of mean is defined like that. U is a function of t. So, mean value is such that ut dt, if we start our investigation at any time t0, then over a time period, for example 1 by t, t0 minus around a time t0, this can be defined as t0 plus t by 2. That means, if I want to find out the mean, this mean is time mean, this mean is time mean, Different means are also described in turbulent flow, but we will consider for this class time mean only. So, time mean value of the time varying component of velocity, fluctuating component of velocity is defined as 1 by t over a time t0, t0 minus t by 2 to t0 plus t by 2 ut dt 1 by t. The t is typically the period of time, and it has been found that the velocity component which is erratically changing with time, that is an erratic fluctuations with respect to time, this is function of time ut. So, if we take the mean, that means if we integrate this over a time period t, where this time period t is sufficiently large to take care of a more number of, to include more number of fluctuations, we get a uniform value, steady value, which is irrespective of the time. So, this is the entire philosophy. That means, if you integrate this time varying quantity, which is varying with time in an erratically irregular manner, its integral 1 by t, that means if we take a time mean value this way over a time period t, which include many more fluctuations, number of fluctuations, we see that this we get a mean value u bar, which means that the velocity ut can be expressed as u bar plus u. That means, it is a can be expressed as a sum of one mean component which is independent of time plus one fluctuating component with this definition. So, it obviously follows that the fluctuating component mean value will be 0. That means, this will be 1 by t u dash t dt over t0 minus t by 2, and t0 plus t is any time period is equal to 0. So, that if we take the mean from both sides, we get u bar is equal to u bar. Why u bar mean is equal to 0? That is, the mean of the fluctuating component will be 0. This is known as Reynolds decomposition. This is known as Reynolds decomposition. Reynolds decomposition principle. Reynolds decomposition principle to specify the velocity field or flow field, specify the velocity field in a turbulent flow, That means, again I tell you that in a turbulent flow, the velocity quantity or any velocity component can be expressed as a mean plus a fluctuating one. This is because the fluctuation is such that this mean can be defined, which is irrespective of the time, by a mean quantity and the fluctuating quantity, so that the mean of the fluctuating quantity is 0. That means, it is a fluctuating velocity is superimposed on a mean value, so that the mean of this fluctuating quantity over a time period t, which includes many more fluctuation, is ultimately 0, so that it can define a mean value. So, this is the Reynolds decomposition principle to specify the flow field. So, now if we specify the flow field this way, then we can now write that u is equal to u bar plus u dash V is equal to V bar plus V dash and W is equal to W bar plus W dash. So, these are all functions of time, for which these are the functions of time. So, a steady turbulent flow is a flow where the mean quantity is independent of time. So, for a steady turbulent flow, the mean quantities are independent of time, but on them there are superimpositions of fluctuating components which are erratical fluctuations or random fluctuations over the mean, whose mean over a time period which include more fluctuations, many more fluctuations, is 0. So, this is the typical expressions of the velocity fields in general in a 3-dimensional coordinates for a turbulent flow. Now, specifications of turbulence, specifications of turbulent flow, specification of turbulent flow, specification of turbulent flow. Now, one specification is the turbulent intensity. What is meant by turbulent intensity? Now, turbulent intensity signifies or specifies the degree of turbulence in the flow field. And as you know, the turbulent intensities are due to that. If this is exactly 0, this is exactly 0, this is exactly 0. So, this is a 3-dimensional laminar flow. So, turbulent flow is because of the presence of this. So, therefore, turbulence intensities can be expressed as some average values of this. These are changing with time, but unfortunately U dash, V dash and W dash is 0. This bar I am using to express the average. This bar means, for example, U bar means the time mean, that is the time means U dt. So, some time interval t0, this is the way I like to replace t0 plus t by. That means whenever I put bar, that means the time mean value. So, time average values of this fluctuating quantity is 0, but because of these random fluctuations, it is so that this bar is not 0, V dash square bar is not 0, square bar is not 0, okay, like our trigonometric functions. That means a periodic function whose mean value may be 0, time mean value, but if you square it and mean it, that is not 0. So, therefore, the turbulent intensity will be represented by this value U dash square, V dash square bar, W dash square bar. That means this average time mean value of the square of the fluctuating components of velocities. So, it is usually defined as turbulent intensity Ti as square root of the mean values of this U dash square bar plus V dash square bar plus W dash square bar. That means the mean values of the arithmetic averages of the mean values of the square of the fluctuating component. So, this is not 0, this is not 0, this is not 0, but these three are not necessarily to be same. Where these three quantities are same is known as isotropic turbulence. Isotropic turbulence. Isotropic turbulence is the case where these values are same. That means this is independent of the space coordinates direction, that this magnitude of this average of time mean value of the square of the fluctuating components, that is their variations are independent of the space coordinates, which means that U dash square is equal to V dash square for isotropic turbulence. That means if the turbulence is isotropic, that means the value this signifies the intensity of the turbulence for the x direction velocity component, intensity of the turbulence for the y direction velocity component. So, individually they are equal. This is for z direction velocity component. So, for an isotropic turbulence, therefore, if we take this here, so we get turbulent intensity is equal to what we get 3 cancels, that means we get U dash square bar square root. That means square root of U dash, that means it is the root mean square value for the fluctuating component. Since we know that U dash bar is 0, U dash bar, for example, in case of an isotropic turbulence, they are identically 0, but this is equal to this and they are non-zero. So, therefore, in isotropic turbulence, this is the turbulence intensity. When this is expressed as a ratio of relative turbulence intensity as a ratio of the free stream velocity divided by the free stream velocity or average velocity in case of a duct flow, or a free stream velocity for flow per solid body. So, this ratio is known as dimensionless parameter as the relative turbulence intensity. So, what is the degree of the turbulence? When we tell that turbulence intensity is very high, that means this value is very high. That means the level of the fluctuating component is very high. So, this is the way we replace the turbulent velocity, turbulent intensity. Now, next I like to tell you the scales of turbulence, scale of turbulence. These are the specifications of turbulent flow, scale of turbulence. Before that, what is correlation coefficient? Correlation coefficient. Now, let us consider the velocity component is a one directional velocity u dash fluctuating component at any time t is equal to 0. Now, the correlation coefficient is defined like this: if we have a fluctuating component of velocity at the same point at a different time u dash t, then the correlation coefficient RT is defined like this: u dash dot u t dash average u0 dash square, similarly ut dash square average. This is the correlation. That means we know that u dash fluctuating component at t is equal to 0, average value is equal to 0. So, fluctuating component at t is equal to t, so the time mean value is 0. But if we make this quantity, that u dash at 0 and u dash at t, product of this, and make a time mean, this is not 0, and this divided by this quantity is the correlation coefficient. This physically signifies that how the fluctuating velocity at an instant t is equal to 0 at any point correlates the fluctuating velocity component at a time t, whether there is a correlation between these two or not. If RT is equal to 0, there is absolutely no correlation, and if RT is equal to 1, that means there is full correlation. That means the fluctuating component at t is equal to 0 whether correlates or has a correlation with the fluctuating component at time t at the same location. So, this is given by this correlation coefficient. Now, at t is equal to 0, there is absolutely correlation, full correlation, RT is equal to 1. So, therefore, if we make a graph of this RT with t, we will see that at t is equal to 0, the correlation is 1. And as we go with infinite time, as the time goes on increasing, the correlation between these two fluctuating components at any instant is just becoming less and less. That means there is no correlation at an infinitely high time. So, there is no correlation between a fluctuating component at time t is equal to 0 with an fluctuating component at the same location after an infinite long time. So, that at t tends to infinity, so this correlation coefficient goes to 0. So, therefore, this integral of this, that means the area of the curve under this t axis, that is the integral of this RT dt 0 to infinity, this gives a finite area because of this nature of this curve. This becomes a temporal characteristics of the turbulent flow. This is a time unit, RT is non-dimensional dt, so this U represents a TL, and if this is multiplied with TL is multiplied with U dash, this gives you a scale L, which is known as Lagrange's scale of turbulence. Scale of turbulence. So, at any instant, at a point, the Lagrange scale of turbulence is given by this quantity. Similarly, if we consider the correlation between the, not here we have considered the correlations between the two velocities at the same point but at different instant. But if we consider the two fluctuating component of velocities at a point r is equal to 0 and another point at r is equal to r, the two different points but at the same time at t, or at t is equal to 0, whatever may be the value of t, that means at the same instant we consider the fluctuating component of velocities at these 2 points, two points at two spatial locations, and one is denoted by u0, another is ur. Then what is the correlation between these two? The correlation coefficient in this case RR in the similar fashion is defined as the product of this time mean value and then the root mean square, well ur dash square. So, this is the, That means if there is correlation between these two velocity components, fluctuating velocity components at a distance r apart, that means two different spatial locations, then RR will be a value which is not 0. But if RR is 0 means there is absolutely no correlation. RR is 1 means there is absolutely correlation. That means when R is equal to 0, that means the 2 points merge to 1 point, so they are totally correlated. This has got 1, and as R goes on increasing, that means if the distance between the 2 points goes on increasing, the correlation becomes less and less, and ultimately there is no correlation between the fluctuating components, fluctuating velocity components for 2 points which are infinitely distant apart. That means R tends to infinity, this is 0. So same thing, this is RR. Now this RR dr, this integral represents the area of this curve under this r axis, and this is known as another quantity L. Let L1, this is known as Eulerian scale of turbulence. Now this scale of turbulence is proportional to the size, of the eddies, This is because the turbulent flow, because of the fluctuations in the flow field, they develop eddies, and the size of the eddies is proportional to this Eulerian scale of turbulence. They determine the size of the eddies, and it is the size of the eddies like this which determines the correlation between the fluctuating components at 2 points. That is the size of the eddy which connects the 2 points and makes the correlation of the fluctuating component of velocities between the 2 points. Now therefore, in short, we can tell now the turbulent flow is a flow where there is an irregular fluctuations of velocity components in a random way in all the directions at any point with time. But this can be expressed as a mean velocity, as a time invariant velocity plus a fluctuating component. Now it happens because of high energy in the flow. Usually the basic origin of the turbulent flow is due to some disturbances. Some disturbances in the flow. It may be in the original reservoir or in the pipe surface, usually in the solid surface, or some solid materials they are in the fluid itself. So from somewhere, due to some disturbances, this thing happens. So what happens, any disturbance in the flow field tries to make a disturbing nature of the flow, for which the flow becomes irregularly varying with time. But due to the viscosity of the fluid, this disturbance is dampened out. It is an inherent nature of the fluid, so that below a certain Reynolds number the flow becomes laminar. That means any disturbances, small disturbances originating from any disturbing sources are dampened out. But what happens when the flow velocity is very high, associated with very high Reynolds number, so fluid particles gets more energy from the main stream with high velocity, so that the disturbances grow rather being dampened out and makes the flow fully turbulent. And it is the Raynaud first who showed that the flow field can be expressed as a time invariant mean quantity superimposed with a fluctuating quantity. So that the time mean value of the fluctuating quantities are 0. So therefore we can write again that the Reynolds decomposition principle, the flow field U is a function of time, can be expressed as U mean plus a fluctuating component. Similarly V, in general, if we expressed in x, y, z coordinate system, x, y, z coordinate system, then rather here u z x, y, same x, y, z coordinate system, we can write u v w is equal to, so that u dash bar is equal to v dash bar is w dash bar 0. That means time mean value is 0. So this is the decomposition principle of the Reynolds. Now we will modify the Navier-Stokes equations with the help of these relationships, or this way, this relationship or these equations for the velocity field. We can now write the Navier-Stokes equation and see that how the Navier-Stokes equations or the equations of motions look like in case of a turbulent flow. I think today time is up, so we will discuss it in the next class.